Let me go down to 2019 question 10 part B. We're going to do the B parts in differential equations. Maybe we'll just do this first part first, and I'm going to get you to try the second part, and I'll put the answer to the second part up tomorrow. We're given this sort of differential equation problem. A particle of mass m, so there's our particle, there's a mass m, and it falls vertically downwards under gravity, so it's falling under the force of its own weight, so that's mg. At time t, the particle has speed v. So at time t has a speed of v, which I'm referring to as the velocity, but it's only going in one direction. So speed and velocity are pretty much the same thing here. Okay, and it experiences a resistance force of magnitude kmv. So it's experiencing a resistance force of magnitude kmv, where k is a constant, and this resistance force is dependent on the velocity. So you couldn't use your sort of linear motion equations here. The initial speed of the particle is u. That means that when the time is 0, the speed of the particle is u. And part 1 says, show that v is the later speed, is equal to g over k minus, so that big monster there. And it's also in terms of u, the initial speed. And you have to use that part, that equation, to work out what part 2 is. So let me work on part 1 and see if you can work on part 2. And note, we're also given a hint in the question. Well, it's not really a hint, it's something you should be aware of, that the integral of dx over a plus b to dx is equal to 1 over b log to the base c of a plus b to dx plus c. So we're going to have to use that at some point in solving part 1. Okay, so let's go on to part 1. Before we do so, let's declare a positive direction to be the direction in which the particle is travelling. Because we're going to use Newton's second law in this, F is equal to ma. F is all the forces acting in the direction of the acceleration, so it's F is mg minus the forces in the opposing direction. They're the forces embedded there, which is kmv, is equal to the mass times the acceleration ma. Okay, so the m's are going to cancel, and that will give me, well, my acceleration, just going to rearrange this, my acceleration a is equal to g minus kv. Well, acceleration is dv dt, the rate of change of velocity, is equal to g minus kv. So that's worth remembering that. So I'm going to have my anything with a v in it to the left hand side, everything else to the right hand side. So if dv all over, I'm going to bring the g minus kv to the opposite side and divide. There we go, and that's equal to dt. Okay, so what am I going to do? I'm going to integrate both sides. There we go. And when I do so, I'm going to bring in the integral that I had there a moment ago. Before I integrate both sides, I'd like the part with the dependent variable v to be positive. So I just rearranged the integral there to give me kv minus g, the v being positive. Doesn't really have to be done, but you know, probably makes it easier to solve the integral. So this ends up being equal to minus 1 over k times log to the base e of kv minus g, and that's equal to t, plus the constant of integration, which is c. Okay, so if you go back to the initial condition there, when the time is 0, the speed is equal to u, all right, the initial speed is u. So therefore we're going to place that in to that equation I've just solved there, where t is 0, t will be allowed to be equal to 0. On the right hand side, that will give me 0 plus c, which is just c. So c will end up being equal to minus 1 over k times log to the base e of k u minus g this time. Okay, and I'm going to place that back in to the equation just before I place that in for c. I'll end up getting t equal to, well, t is equal to minus c this time, which is 1 over k times log to the base e of ku minus g minus 1 over k times log to the base e of kv minus g. Okay, that will imply, well, effectively we've just got an equation now. We've effectively got everything we need here. We'll have t is equal to 1 over k times log to the base e of ku over minus g, all divided by kv minus g. And I've got an equation. I'm just going to have to isolate the v, and hopefully when I do this, I'll get what I'm required to find. So t will be equal to log to the base e. I'm going to multiply both sides by k here. I've just slightly rearranged the equation also. So now I'll use one of my log rules. E to the kt will be equal to ku minus g divided by kv minus g. Okay, so kv minus g, multiplying both sides by kv minus g here, is times e to the kt is equal to ku minus g. Alright, so I've got kv minus g is going to be equal to ku minus g divided by e to the kt. Trying to isolate v here. That's equal to ku minus g by e to the minus kt, bring the e up and changing the sign of the index. And that will imply that kv will be equal to ku minus g by e to the minus kt plus g. Okay, so that's superb. I'm very close to getting v now. V will be equal to what I'm going to divide across by k here. I'll get ku minus g by e to the minus kt divided by k plus g over k. And when you rearrange that first term there, you will get this equal to g over k minus g over k minus u times e to the minus kt, which is effectively what I was asked to prove.